Today I wanted to do a reaction video on Arvin Ash's video on how inflation theory fixed the Big Bang. And I hate to pick on Arvin Ash all the time, but he makes videos that are very constructive on what's wrong with standard models in physics. And in this case, you have to start with the problem that it doesn't take the quantum field into account. The quantum field and quantum fluctuations exist. And in quantum field theory, there's no boundary either in dimensions, distance, or time, like infinity, into how long it's existed or how big it is. So for all purposes, we have to treat it like it's infinite, unless someone can come up with a theory to say how it's not infinite. And then because quantum fluctuations have wavelengths and frequencies, distance and time emerge from the quantum field. And because quantum fluctuations rotate to form electric and magnetic fields, the electric and magnetic constant, the permittivity and permeability, come from it. And they cause the speed of light, because the speed of light is a function of the permittivity and permeability, and every other physical constant. So once we have the quantum field in place, we have the speed of light limit in place. So objects can't exceed the speed of light limit from the very start, and it's infinite in extent. And so the quantum field is where the dimensions and clock rates come from. They don't come from space. Space by itself doesn't have any dimensions or clock rates. And with that, I'll show you his introduction.
You probably know this familiar story. In the beginning, the universe was packed tightly together into a point of infinite density. It then exploded into the universe we see today. This is commonly thought of as the Big Bang. Astrophysicists will tell you that this image we have of the Big Bang is incorrect. First, there was no explosion like a grenade where all kinds of shrapnel goes flying away. There was no substance like stars or galaxies or even atoms that went flying. The entire universe itself expanded and became bigger. Atoms only coalesced a few 100,000 years later as temperatures cooled, and larger structures took much longer to form. The Big Bang was not when the universe had zero size or infinite density. It is just a moment in time when the universe was very hot and very dense. And the Big Bang did not happen at some special point in space, but everywhere in the known universe at the same time. And contrary to popular belief, the Big Bang model is not a theory of how the universe began. Science doesn't currently tell us how or why the universe came to exist or what caused it to start expanding. The Big Bang model is about events that happened in the early universe, which led to the universe we observe today. That history is well understood and has been verified by evidence that we can observe even today, 13.8 billion years later. But up until the 1980s, this model failed to explain some other observed properties of the universe, which remained puzzles, like why is it so homogeneous, why its geometry appears flat, and why there are no magnetic monopoles. Along came the theory of cosmic inflation proposed by Alan Guth and others, which solved many of these puzzles and is today considered by most physicists to be a standard part of early Big Bang cosmology. What is this theory of inflation? How does it solve some of the most nagging cosmological puzzles? And what causes it to happen? That's coming up right now.
Now Arvin begins quoting the Bible saying, in the beginning, when the beginning is a fallacy. Determinism and causality require that there be a cause for each effect, going indefinitely back in time, which requires a universe that's infinitely old, because there's no way to start a universe without an initial cause. So the idea of a beginning is a fallacy. And it also violates the principle of conservation of energy. And then you have the nothing problem, which I'll talk about some, in that they have the Big Bang theory starting with nothing, because particles aren't produced till later. And there's only thing there is quantum fluctuations. But quantum fluctuations don't have heat, and they don't have density. So when they say it's hot and dense, what's hot and dense? There's nothing there. It's a theory that only a mathematician or a deeply religious person could love, because it's not based on any physical reality. And then he claims there's lots of evidence for it, but it's all based on circular logic, like a lot of standard model physics. In that if you assume it's true and you massage the data enough so it matches your theory, then you turn around and say that the data supports the theory, after you've completely twisted and distorted it and massaged it to force it to fit the theory. And so that's the way physics works today. Now he states 3 problems: that the universe is homogeneous, flat, and has magnetic monopoles. And as far as being homogeneous, you started with the quantum field because it was always there, no matter how the matter got there. And the quantum field's homogeneous, so that's how you get homogeneity. And the quantum field is geometrically flat, so that's how you get flatness. And he doesn't say in any of these videos that, oh, by the way, if you measure the flatness, which we have, and you determine how old the universe would have to be for it to be as flat as it is, well, it's 92 billion years. The universe would have to be 92 billion years old in order to be as flat as it is. And that's if things are moving at the speed of light. If they're moving at a fraction of the speed of light, it really has to be trillions of years old to be as flat as it is, because most galaxies are moving less than 1,000 kilometers per second. So the idea of saying, oh, it's not flat, but it looks like it's flat because of inflation. They have it magically inflate really fast, although it can't do that because the quantum field already exists and it prevents it from inflating. And then the last is, oh, there should be magnetic monopoles. Well, no, there shouldn't. Actually, this is kind of a separate problem from the Big Bang problem, is that they decided to include magnetic monopoles for no good reason, because magnetic monopoles are not in Maxwell's equations. The thing is, with quantum fluctuations, they're dipoles. So when a quantum fluctuation forms an electric field, the quantum dipoles align with the field. They're polarized. And by polarizing, you create the electric field. Well, when quantum dipoles rotate, they make a magnet. You rotate this way and you get a north and a south pole. So a rotating electric charge dipole always has a north and south pole, so there's no magnetic monopoles. And another important point is the quantum field can't expand. It has its dimensions. And so, as I said, we have to start with dimensions being there for infinity. It's not something that can be altered. And these quantum fluctuations are constantly present, they're constantly interacting. The quantum field has an infinite energy density without having heat and without having a matter or material density. We can't measure the density of quantum fluctuations, and we can't measure the heat of the quantum fluctuations. So there's nothing hot and dense there when only the quantum field is present. Not that we can measure in the way we measure air pressure and heat. You have to have matter first. So if you have a theory where matter is produced later, then there's nothing that's hot and dense. And with that, I'll play the second clip.
Specifically, the questions left unanswered in the model were, why was the early universe so uniform? Why is the universe so close to being geometrically flat? And why do we not see any magnetic monopoles, which could theoretically exist? The simplest version of the theory of inflation says that the universe expanded exponentially fast, faster than the speed of light, near its earliest history, from what is believed to be the beginning of the universe, from about 10 to the negative 36 seconds after the Big Bang to 10 to the negative 32 seconds. During this time, it expanded a factor of at least 10 to the 78, going from being very small to being exponentially large in comparison. You might be thinking, I thought things couldn't move faster than the speed of light. Einstein's theory of special relativity shows that this speed limit applies to things moving within space, but not the expansion of space itself. So this is permissible. The universe today is expanding, but galaxies aren't actually moving at that expansion rate. Only the space between galaxies is becoming larger, and only on very large scales. Gravity also plays a role so that on smaller scales, gravity still holds stars together within a galaxy, and certain nearby galaxies are still attracted to each other, like the Andromeda galaxy is to our Milky Way galaxy. While the whole universe may come from a tiny volume of space, cosmic inflation would have caused all points within that space to expand. And this expansion, or inflation, happened everywhere in space. There is no center of the universe or location. Every point moved away from every other point. Expansion faster than the speed of light during inflation also means that these points, while they may have been causally connected initially, would have moved apart after inflation such that they became causally disconnected. This is because causality is limited to the speed of light. No information can travel faster than this speed. As a consequence of this, there are certain parts of the universe that we will never be able to see or detect in any way because any light or gravity coming from it will never reach us.
Well, this clip is sort of worst hits of the next 5 minutes of video, and where he makes a lot of misstatements. And he doubles down on nothing has heat and density, and it expands into nothing. And then there's outside the balloon, there's a different sort of nothing that is a nothing that doesn't even exist. So it's a super nothing. Well, and which is a false assumption. All the space in our universe that we observe has quantum fluctuations, and all space is space. There's no space that isn't even space, and there's no nothing in quantum fluctuation theory, quantum field theory, going back to Max Planck. There's no zero energy state. There's no state of nothingness ever. There's always quantum fluctuations present. And so the premise at the beginning of the Big Bang of having space that isn't even space that the universe could grow into is false. The quantum field is infinite and is there for an infinite amount of time into the past, so you have to deal with it. You don't have this balloon model. It's just crazy. And so you can't exceed the speed of light because the quantum field determines the speed of light. So the speed of light limit for bodies of matter is already in place the whole time, and the dimensions are already in place the whole time. So you can't have space expand, space being non-physical anyway. It only gets its physicality from the quantum field. So there's no faster than light expansion of space. And then he brings causality into it, which I don't really want to go into. But everything has a cause. There's always a cause and effect. And with that, I'll play the third clip.
Now, let's see how inflation could explain the three problems of the Big Bang model: the observed homogeneity, the flatness issue, and no observed magnetic monopoles issue. When we look out into space, we see that the universe, on large scales, is pretty much uniform. The universe is extremely homogeneous and isotropic, which is just a physics jargon for saying it appears roughly the same everywhere you look. This can also be seen in the cosmic microwave background, or CMB, where the tiny differences you see on this image represent temperature fluctuations of at most only 0.0001 Kelvin, or less than 1/10,000th of 1 degree. To see how inflation explains why the early universe was so uniform, let's imagine that before inflation, the universe was completely random. Maybe in one place the density was very high, and a fraction of a millimeter off to the side, the density was very low. You can imagine it like the surface of a deflated balloon. There may be tiny imperfections like different thicknesses and wrinkles randomly distributed on it. Now imagine that this balloon is suddenly inflated to a very large size. A tiny fraction of a second later, the wrinkle in the balloon surface gets smoothed out. Any density differences of the balloon's skin become diluted. This is analogous to what happened during inflation as a tiny volume increased by at least 10 to the 78x. Now let's look at the flatness problem. Imagine living like an ant on the surface of a very small balloon. It would be a two-dimensional world. But if the balloon was tiny enough, it might be obvious to you that this surface was curved and that you were living in a closed or curved universe. However, if that ball was expanded to the size of the Earth, it would appear flat to you, even though it is still a sphere on much larger scales. Now scale that up to human size and the ball being much larger than even the observable universe. To you, it would appear to be flat as far as you could see, even though it might have been obviously curved to start with. Inflation stretches any initial curvature of the three-dimensional universe to near flatness. We don't know if the universe is 100% flat, but if there is curvature, it is so small that we can't measure it with our current technology. Note, how does inflation solve the monopole problem, the fact that we can observe no magnetic monopoles in the universe? Well, monopoles can only theoretically form at very high temperatures, the kinds of temperatures that were only present during the Big Bang. But once they formed, they should be stable enough to survive. The idea is that inflation would have quickly cooled down the universe because of rapid expansion, and only monopoles created prior to inflation would then continue to exist in the universe. But during inflation, the density of monopoles would drop exponentially, so their abundance would drop to undetectable levels because they would exist in such low densities.
Okay, in this section, he gets to the heart of the problem, basically repeating his 3 points in more detail. And he brings in the cosmic microwave background, which is very homogeneous to an extremely large degree. We have great evidence that there's matter in the universe that's producing this light. It must be. And it's very homogeneous to begin with, which matches the quantum field being homogeneous. And then he gives us the ant on the balloon problem. Would the ant realize that it's on a curved balloon? Or like if we're walking around Earth and Earth looks flat, do you decide that Earth must be flat even though it's curved? And so that's been used as an example all along with general relativity. But as I said before, in order to explain the flatness, the universe would have to be over 90 billion years old, which is much older than the Big Bang model allows, because the universe really is limited to the speed of light. It can't exceed it. And then he talks about monopoles again, which is an entirely nonsense theory, so trying to come up with this complicated explanation for why we don't see magnetic monopoles. No, it's a simple explanation. We don't see monopoles because they never existed. They only exist in a mathematical fiction, not in the real world. If there were particles that had a north or a south separately magnetic pole, we would have observed them. We would have observed them long ago. But north and south poles happen when particles move, and the dipoles of the quantum field have north and south poles. So north and south poles are always present. So these three problems are easily fixed if you stick with quantum field theory. The only way you can get yourself in this mess is if you ignore quantum field theory completely, which he does. Now he goes on and has a couple more minutes of video where he goes into some even deeper things, and I decided not to even cover that. But you can watch this video if you want and compare it to what I've been telling you. Well, I hope you liked the video, and if you do, hit the like button and share it with your friends and subscribe for my next videos. And if you're interested in learning more about my research, I have a few books for sale, and you can learn a lot about quantum field theory or particle theory from one of them. So thanks for watching.